Every day, billions of AI requests are answered in just a few seconds. Whether you're chatting with an AI assistant, generating an image, translating a language, or analyzing data, it all feels effortless. It seems as though artificial intelligence exists somewhere in the cloud, floating invisibly across the internet. But the reality couldn't be more different. Behind every response is an enormous physical infrastructure built from steel, copper, water, electricity, and some of the most advanced cooling systems ever engineered. Today, we're going behind the scenes to uncover the hidden machines that keep artificial intelligence alive. This is where AI really lives. Inside these massive buildings are thousands of server racks filled with powerful processors working continuously, day and night. Modern AI data centers consume enormous amounts of electricity, often hundreds of megawatts, and every watt eventually becomes heat. These facilities are carefully engineered environments where computing power, electrical infrastructure, networking, and cooling systems all operate together as one integrated machine. Without this infrastructure, modern artificial intelligence simply wouldn't exist. At the heart of every AI server is the graphics processing unit, or GPU. Unlike traditional processors, GPUs contain thousands of small computing cores designed to perform millions of calculations simultaneously. This parallel architecture makes them ideal for training and running today's advanced AI models. But extraordinary computing performance comes at a cost. As electricity flows into the GPU, almost all of that electrical energy is converted into heat. Every AI prompt begins this invisible transformation from electrical power into thermal energy. Heat is the greatest enemy of high-performance computing. As billions of transistors switch on and off every second, temperatures inside the GPU rise almost instantly. If this heat isn't removed quickly, it spreads through the processor, surrounding electronics and server chassis. Excessive temperatures reduce efficiency, shorten equipment life, and threaten the stability of the entire system. Every AI response therefore begins with an engineering challenge, removing heat as fast as the processors generate it. Without cooling, AI servers would rapidly become unstable. As temperatures climb, processors automatically reduce their operating speed in a process known as thermal throttling. If temperatures continue rising, components may begin shutting down to protect themselves from permanent damage. Left unchecked, an entire AI cluster could go offline. That's why every modern AI data center invests as much engineering into cooling infrastructure as it does into computing hardware. In many ways, cooling isn't simply supporting AI, it is what allows AI to exist in the first place. Our journey begins inside the cold aisle. This carefully engineered corridor is where chilled air first enters the server room. Powerful air handling units continuously deliver cool, filtered air into this space, maintaining a stable environment for thousands of AI servers. Every rack is positioned so its intake faces the cold aisle, ensuring each processor receives the coolest possible air. This isn't accidental. It is the result of precise engineering designed to maximize cooling efficiency while minimizing wasted energy. Here, the invisible battle against heat truly begins. As cool air enters the front of each server, high-speed fans immediately pull it across the internal components. The airflow is carefully directed over the GPUs, CPUs, memory modules, voltage regulators, and power electronics. Each component transfers its heat into the moving air through metal heat sinks with hundreds of thin fins that dramatically increase the cooling surface area. Within just fractions of a second, the once cool air absorbs enormous amounts of thermal energy. By the time it reaches the back of the server, it has become significantly warmer, carrying away the heat generated by artificial intelligence. The warmed air exits every server into the hot aisle. Unlike the cold aisle, this corridor is intentionally designed to collect concentrated heat from thousands of machines operating simultaneously. Keeping hot air separated from cold air is essential. If the two streams were allowed to mix, cooling efficiency would collapse, energy consumption would increase, and server temperatures would quickly rise. Many modern AI facilities use physical containment systems, doors, and ceiling panels to isolate these airflow paths, ensuring the hot air continues moving toward the next stage of the cooling process without contaminating the cold supply. The hot air now reaches one of the most important machines inside the data center, the Computer Room Air Handler, or CRAH, and in some facilities, the Computer Room Air Conditioner, or CRAH. Large fans pull the hot air through specially designed cooling coils inside these units. At this moment, the journey changes. Up until now, heat has been traveling through air. But inside the CRAH, that heat is transferred into a completely different medium: water. The air itself never creates the cooling. Instead, it simply delivers heat to the chilled water system hidden inside the building. This is the turning point of the entire documentary. Inside the cooling coil, thousands of thin metal tubes carry chilled water supplied by the central cooling plant. As hot air passes over these tubes, thermal energy naturally flows into the colder water circulating inside. The air rapidly cools and is sent back to the cold aisle, ready to cool the servers once again. Meanwhile, the water leaves carrying the captured heat toward the mechanical plant. From this point forward, we're no longer following moving air. We're following heated water as it begins its journey through pumps, heat exchangers, industrial chillers, and cooling towers, where the heat generated by AI will finally be released back into the atmosphere. Now that the heat has been transferred into the water, our journey leaves the data hall and enters the mechanical plant. Here, enormous industrial pumps become the driving force behind the entire cooling system. These pumps operate continuously, pushing thousands of gallons of chilled water every minute through a vast network of insulated pipes. Without them, the cooling loop would stop. Heat would remain trapped inside the data center, and AI servers would begin overheating within minutes. Although they rarely receive attention, these pumps are the beating heart of the cooling infrastructure, ensuring heat never stops moving away from the processors. As the warmed water flows deeper into the cooling plant, it reaches another critical piece of equipment: the heat exchanger. Its purpose is simple but essential: transfer heat from one water loop to another without allowing the two water supplies to mix. Thin metal plates or tubes create a large surface area where thermal energy naturally flows from the hotter circuit into a cooler one. This separation improves system efficiency, protects sensitive equipment, and allows different parts of the cooling network to operate under their own optimized pressures, temperatures, and water chemistry. The heat itself continues its journey, moving from one loop to the next while the water remains isolated. The warmed water now arrives at the industrial chiller, the largest and most powerful cooling machine in the entire system. Inside the chiller, a refrigeration cycle works continuously to remove the heat carried by the water. Compressors increase the pressure of the refrigerant, condensers reject heat, expansion valves lower the pressure, and evaporators absorb thermal energy from the returning water. This closed refrigeration cycle transforms warm return water back into cold supply water that can once again cool the AI servers. Every second, industrial chillers remove enormous amounts of heat, allowing thousands of GPUs to continue operating at full performance around the clock. Although the chiller cools the water, the heat itself still has to go somewhere. That responsibility belongs to the cooling tower. Located outside the building, these towering structures release the captured thermal energy into the atmosphere. Warm condenser water is distributed across specialized fill material, while large fans pull air upward through the tower. A small portion of the water evaporates, carrying away significant amounts of heat in the process. This natural principle of evaporative cooling allows the remaining water to return at a much lower temperature before circulating back through the chiller. The heat generated inside millions of AI calculations has now completed its journey from microscopic computer chips to the open air. Before the cooling water can begin another cycle, it must be carefully maintained. Water treatment systems continuously monitor and control water quality to prevent corrosion, mineral scaling, biological growth, and contamination inside the cooling equipment. Filters remove suspended particles, chemical dosing systems maintain proper water chemistry, and advanced monitoring equipment checks conductivity, pH, and microbial activity. Even a thin layer of scale inside a heat exchanger can significantly reduce cooling performance and increase energy consumption. Clean water isn't simply a maintenance concern, it is a critical engineering requirement that protects billions of dollars of AI infrastructure while ensuring the entire cooling system continues operating efficiently for years to come. By now, we've seen how heat travels from the AI processors through air, water, and the central cooling plant. But none of this infrastructure could operate safely without continuous monitoring. Throughout the data center, thousands of sensors constantly measure temperature, pressure, water flow, humidity, vibration, electrical load, and water quality. Every pump, chiller, heat exchanger, cooling tower, and server rack continuously reports its condition in real time. These sensors form the nervous system of the entire facility, providing operators with instant visibility into every part of the cooling process. If even a small change occurs anywhere in the system, it is detected almost immediately. Collecting data is only the beginning. All of this information flows into the Building Management System, or BMS, the hidden brain that coordinates the entire cooling infrastructure. Every second, sophisticated control software analyzes thousands of sensor readings and automatically adjusts pump speeds, valve positions, fan operation, water temperatures, and chiller capacity to match the changing demands of the AI workload. As processors become busier, cooling increases automatically. As demand falls, the system reduces energy consumption while maintaining stable operating conditions. Rather than relying on constant human intervention, the cooling plant continuously optimizes itself, balancing performance, reliability, and energy efficiency across the entire facility. In AI infrastructure, reliability is never left to chance. Every critical component has a backup. This engineering philosophy is known as redundancy, often described as N+1 design. If one chiller requires maintenance, another is already available. If a pump fails unexpectedly, an identical backup immediately takes over. Additional cooling towers, water loops, electrical feeds, and control systems stand ready to maintain uninterrupted operation. Although many of these backup machines may appear idle during normal operation, they are constantly tested and maintained so they can respond instantly whenever needed. The goal is simple. AI must never stop because a single piece of equipment fails. When a failure does occur, speed becomes critical. Imagine one industrial chiller suddenly shutting down. Within seconds, the building management system detects the problem, isolates the failed equipment, starts a standby chiller, reroutes water flow through alternate piping, adjusts pump speeds, and restores cooling capacity, all automatically. This process, known as automatic failover, allows the cooling system to continue operating without interrupting the AI workloads running inside the data center. Most users around the world never notice that anything happened because the infrastructure was designed to recover before temperatures have a chance to rise significantly. But what if every layer of protection fails? Imagine the cooling system shutting down completely. Within seconds, temperatures inside the GPUs begin climbing rapidly. Server fans immediately accelerate to their maximum speed in an attempt to remove more heat. As temperatures continue rising, processors reduce their operating frequency through thermal throttling to protect themselves. If cooling is not restored, automated safety systems begin shutting down servers to prevent permanent damage. Left unchecked, entire AI clusters and eventually entire data centers could go offline. This is why cooling isn't simply another utility inside an AI facility. It is the invisible infrastructure that determines whether artificial intelligence can continue thinking, learning, and serving billions of users around the world. For decades, air has been the primary method of cooling computers. But today's AI processors are producing so much heat that air alone is no longer enough. The next generation of AI infrastructure is moving toward direct-to-chip liquid cooling. Instead of cooling the entire server with moving air, specially engineered cold plates are mounted directly onto the processors. Coolant flows through tiny internal channels, absorbing heat exactly where it is generated before carrying it away through a closed liquid loop. Because liquids transfer heat far more efficiently than air, this approach supports faster processors, denser server racks, lower fan power, and significantly improved energy efficiency. As AI models continue growing, direct liquid cooling is rapidly becoming the new industry standard. Some engineers are taking cooling one step further. Rather than circulating liquid through cold plates, entire servers are submerged inside specially designed tanks filled with dielectric fluid, a liquid that safely surrounds electronic components without conducting electricity. Heat moves directly from the processors into the surrounding fluid, eliminating the need for many traditional fans and airflow systems. The warmed liquid is then circulated through external heat exchangers, where it is cooled before returning to the tank. Immersion cooling offers exceptional thermal performance while reducing energy consumption, noise, and mechanical complexity. It represents one of the boldest innovations in the evolution of AI infrastructure and demonstrates how dramatically data center design is changing. As artificial intelligence continues expanding, individual server rooms are evolving into enormous AI campuses. These facilities are becoming complete industrial ecosystems, combining massive computing halls with dedicated electrical substations, mechanical cooling plants, water treatment facilities, cooling towers, backup generators, battery systems, and advanced network infrastructure. Some of the newest AI campuses are designed to consume as much electricity as entire cities while supporting hundreds of thousands of GPUs working together. Building these AI gigafactories requires the same level of engineering coordination found in airports, refineries, and power stations. The future of AI is no longer measured only in computing power. It is measured in infrastructure. The next chapter of AI cooling is already taking shape. Engineers are developing smarter cooling systems that use artificial intelligence to optimize their own operation, predicting workloads before they occur, and adjusting equipment in real time. Higher density server racks, warmer water cooling loops, advanced refrigerants, modular cooling plants, and large-scale heat recovery systems are transforming how data centers are designed. Instead of simply removing waste heat, future facilities may reuse it to heat nearby buildings or support industrial processes. As processors become more powerful, cooling will become an even more critical part of AI innovation, driving new advances in efficiency, sustainability, and infrastructure design. Our journey began with a single AI processor generating heat. We followed that heat through server fans, cold aisles, hot aisles, air handlers, chilled water loops, pumps, heat exchangers, industrial chillers, cooling towers, intelligent control systems, backup infrastructure, and finally into the next generation of liquid cooling technologies. What appears to be a simple AI response is actually supported by an extraordinary network of hidden engineering systems working together with remarkable precision. At Renee Energy, our mission is to reveal the hidden infrastructure that powers modern civilization. From AI data centers and advanced cooling systems to hydrogen, clean energy, industrial machines, and the technologies shaping our future. If you enjoyed this journey, explore even deeper engineering insights with H2 Hub by Renee Energy, where complex industrial systems become clear, connected, and understandable. Because behind every breakthrough technology lies an even greater engineering story waiting to be discovered.